Welcome, my name is Dr. DrWedding, and this is DrWedding, DC09. The voltage divider rule. In this video you will learn what the voltage divider rule is, and how to use it to find the voltage drops across resistors in series. This will be followed by 3 very easy problems used to demonstrate how to use the voltage divider rule. Lastly, a 4th problem is covered that is more complex. This is used to demonstrate a more realistic problem you may encounter. The voltage divider rule is not a law like Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. A law will always work and will work for every circuit. A rule will work in certain types of circuits. The voltage divider rule will help you calculate the voltages across the resistors in a series circuit, or the voltage across part of a circuit that has a section that has resistors in series. It will not work with resistors in a parallel circuit or resistors in a series parallel circuit. The voltage divider rule equation is: the voltage across a resistor is equal to a fraction of the total voltage, where the fraction is the resistor divided by the total resistance. The voltage divider rule is just Ohm's law in disguise. But unlike Ohm's law, the voltage divider rule only works on series circuits. Let's prove these 2 equations are the same. Start with the voltage divider rule. By putting V total over 1, it becomes a fraction without changing its value. The 2 fractions are combined by multiplying the numerators and multiplying the denominators. V total divided by R total is equal to I total. So the equation becomes: the voltage across a resistor is the total current times the resistor value. By assuming the current through all of the resistors is the same as the total current, is why this equation only works with a series circuit. So the voltage divider rule is just a specialized version of Ohm's law that has limited use. You may be wondering why you would need the voltage divider rule if it only works with a series circuit, when you have Ohm's law that works with every circuit. This is a good question. There are a few reasons to learn it, but here are 2 reasons. Reason 1. It teaches you an important concept about a series circuit. If you understand the voltage divider rule, then you will start to get a feel for a circuit by just looking at it. You will know that all of the resistors will have some voltage drop across them. You will also know that the largest resistor will have the largest voltage drop, and the smallest resistor will have the smallest voltage drop. Reason 2. It will help you take shortcuts when you are solving more complex circuits later in the course. The voltage divider rule gives you the voltage across all of the resistors without having to calculate the total current. This can save steps if you only need to find a single voltage, like when you are trying to find a Thevenin voltage later in this course. Now you may be wondering, why are we covering it now, if it will help us later? Why not cover it later? This is also a good question. VDR is easy to understand and learn when you see it working on a very simple circuit. If you were learning how to compress and expand a series parallel circuit in order to find the Thevenin voltage, then VDR would just get lost in a long lecture. Learning it now will make future lectures shorter and easier to understand. Let's try the voltage divider rule out on a circuit. The circuit above was solved in the previous video when series circuits and Ohm's law were covered. The same circuit will be used to demonstrate the voltage divider rule. The solutions from the previous video will be compared to the solutions generated by using the voltage divider rule. In the circuit above, find the voltage across R1 using the voltage divider rule. Start by writing down the voltage divider rule equation. To calculate the voltage across R1 using the voltage divider rule, you need R total and V total. In a series circuit, V total is the supply voltage. So, V total equals 12 volts. In a series circuit, our total is the sum of the resistors. So our total equals 150 ohms plus 250 ohms for a total of 400 ohms. To find the voltage across R1, substitute 150 ohms in for the resistance R. By solving the equation with 150 ohms in for the resistance, you will find the voltage drop across R1 is 4.5 volts. This value matches the value that was calculated in the last video. Furthermore, now that you have the equation with R total and V total, the equation can be used to find the voltage across R2. So that will be our next step. Using the circuit above, find the voltage across R2 using the voltage divider rule. We have already calculated the total voltage and total resistance for this series circuit. So this equation can be reused to calculate the voltage drop across the second resistor in this circuit. By substituting 250 ohms in for R and solving the equation, you will find the voltage drop across R2 is 7.5 volts. The values that were calculated using the voltage divider rule match the values that were calculated in the last video. You can also see the largest resistor has the largest voltage drop, and the smallest resistor has the smallest voltage drop. Here is a second example. This example was also solved in the previous video. Using the circuit on the right, find the voltage across R1, R2, and R3 using the voltage divider rule. You may wish to pause the video and see if you can solve it on your own. After you are done, you can restart the video for the solution. Start by writing down the voltage divider rule. Find V total and R total. V total is the supply voltage, and in this circuit the value is 25 volts. R total is the sum of all the resistors. In this circuit, our total is 1,250 ohms. These values can be plugged into the voltage divider rule, and it will generate an equation that will be used to find the voltages across all three resistors. To find R1, use 200 ohms for the resistance, and you will find that the voltage across R1 is 4 volts. To find R2, use 400 ohms for the resistance, and you will find that the voltage across R2 is 8 volts. And to find R3, use 650 ohms for the resistance, and you will find that the voltage across R3 is 13 volts. These values match the values that were calculated in the last video. As you can see, the largest resistor has the largest voltage drop, and the smallest resistor has the smallest voltage drop. Here is the third example, and as in the previous two examples, this circuit was already solved in the previous video. Using the circuit on the right, find the voltage across R1, R2, and R3 using the voltage divider rule. You may wish to pause the video and see if you can solve it on your own. After you are done, you can restart the video for the solution. Start by writing down the voltage divider rule. Find V total and R total as before. These values can be plugged into the voltage divider rule. Use this equation to find the voltages across all three resistors. As before, substituting the resistor values into the equation, one at a time, will give you the voltage drop across each of the resistors. These values match the values that were calculated in the last video. And as before, the largest resistor has the largest voltage drop, and the smallest resistor has the smallest voltage drop. Here is the fourth and final example. This circuit is more complex and is used to demonstrate a real-world application of the voltage divider rule. Assume you are going to solve this series circuit for all of the unknown values. If you make a table and fill in the unknown values, you will notice a problem. You do not have two values in any of the rows, so Ohm's law will not help you. You are missing one of the resistor values, so you can't find the total resistance. And you do not know any of the currents, so the current being the same everywhere does not help. At this point, you may think there is not enough information to solve the circuit, but there is. You can use the voltage divider rule to perform some of the calculations without the use of the current. As in the previous examples, you need to find V total and R total. V total is the supply voltage, and in this circuit the value is 10 volts. R total is the sum of all the resistors, but one of the resistor values is unknown. But that is not a problem. Just write the total resistance as R1 plus 17 k ohms. This will generate the equation at the bottom of the screen. Start with this generic equation. Plug in the information for R1. Unlike the previous examples, this time you know the voltage across R1 is 1.5 volts. But you do not know the resistance of this resistor, so you just use the variable R1 to represent its resistance. At this point, you have one equation and one unknown, so finding R1 is just algebra. The steps to isolating R1 are as follows. Divide both sides by volts. This will eliminate the voltage on both sides of the equation. Bring the 10 to the numerator on the right side of the equal sign. Cross multiply, so the 1.5 is multiplied by the quantity R1 plus 17 kilo ohms, and 10 R1 is multiplied by 1. Distribute the 1.5 into the parentheses. Subtract 1.5 R1 from both sides of the equal sign. Isolate R1 by dividing both sides by 8.5. The voltage divider rule has been used to find R1. R1 is equal to 3 k ohms. By adding this value to the table, the solution to this circuit becomes easy. With the 3 resistors, you can find the total resistance. You can use Ohm's law to find the total current or the current through R1. In this example, the total current was calculated. Current is the same throughout the entire circuit, so it can be copied to all the boxes in this column. Use Ohm's law to find the voltage across R2. And use Ohm's law again to find the voltage across R3. Once the table is completely filled in, the information can be added to the original circuit. Hopefully this video has taught you what the voltage divider rule is and how to use it. The voltage divider rule will be used to solve more complex problems later in the course. If you find these videos helpful, please like the video, leave a comment, and subscribe to my channel. This is the only way I can continue to make these videos.